Hey there, Alch 2. Before we can do some things, we're going to jump to chapter 6, and we're going to talk about exponents and how we work with those and square roots as we get through all of the stuff. But we need to review our exponent properties, and I know this was just before we had some messed up times last year. So I just want to check in and make sure we're okay with it. So we have product rule is the first thing we're going to get into. But before we can even get into that, we know that these both end up with a product, right? This is 3 times x. And is that the same thing as x to the third power? We know that is not the same, right? Because 3 times x is 3 of that x, and then this is x times x times x. So they're definitely not going to be equal in most cases, right? We could make some cases where it definitely is, but I can't think of one off the top of my head. Maybe when it's 0, right? That would work out. Okay, so remember this was 1 and 1 and 1. So what happens is we get to add these up and make it x to the third. And that's what we're going to deal with, some of this repeated multiplication. Now, I don't want you to spend too much time in this repeated multiplication because if you write 3 times 3 times 3 times 3, and we're going to use that as 3 times 3 times 3 times 3 times 3, like this is going to bore us all to tears. So how can I shortcut that? And that would give me the product rule. And that means that if I have the same base, so in this case, that's the 3, right? That's the base. The 4 and the 5 are my exponents. If I write them all out, how many of those 3's did I end up with? And that's if I add them together, I get 9. So that's what we're trying to shortcut all these. So I'd like to go from here, say the base is 11. How many 11's did you end up with? So we had 6 here and 8 there. So that's 11 to the 14th power. Here we had 3 of them, so it's a 5, that's 4 more, so that's 5, 6, 7, 8. So this is 5 to the 8th power. And if we can say that we're going to do this for variables as well, so if I have 9 x's and I have 7 x's, how many x's do I have? I have 16 for the grand total. So what's the rule? So the rule is if I have x to the nth power times x to the mth power, right? Often we switch out to m and n for that. What should I do with those? I should add them. Okay, so why do you think it's called the product rule? Well, we are using multiplication to do that addition, right? Remember, those two things kind of go together. Okay, so we want to come up with a rule that come up with this class. All right, so we have this one here, but maybe you do 5 to the 7th times 5 to the 8th. So that's 5 to the 15th, just so that we have one in numerical sense as well. And I might even go through and say, you know what, that's because I want to add these because I have the same base. That's rule number 1. All right, so some things I'm going to do is this exponent should be distributed if I have things being multiplied in here. This is only in multiplication. Okay, so I can't stress that enough, as I'll be fixing that from time to time. So we do end up with 4 to the 4th, 6 to the 4th, and I do want to multiply those. This is x to the 5th and y to the 5th. Okay, so that means, and this is the one we really want to get to. That means I should get 3 to the 6th and x to the 6th. Now 3 to the 6th we could get numerically through our calculator, but I just want to make sure that that 6 is being distributed to the things in there, and that will happen soon as we also deal with this in a fraction as well. Why do we call it distributive rule? Because it's very similar to having 3 times x plus 4 that I want to distribute to those things. Okay, but keep in mind that for this one, if I had x plus 6 and I want to take that to the third, okay, that goes back to that beginning understand. This does not get distributed, right? This means I need x plus 6 times x plus 6 times x plus 6. So this is only going to be a rule for exponents when we are multiplying the items in there. All right, we didn't study rule yesterday, so how's this look? All right, so 5, let's go x to the, let's just go with 5 and x, right? Because we didn't talk about anything else yet. And let's use that to the third power. So this is 5 to the third, x to the third. So we're going to distribute that in. All right, for quotients, what should I do, right? So the multiplication turned into addition. So it looks like as I get rid of these 2's and these 2's, right, I'm subtracting these 2's out. So 3 minus 2 gives me this 1 over here. So it seems like a rule that I could follow, right? Because if I had 7 3's on top and I had 4 on the bottom, I would have 3 3's left over and they would be on the top. Okay. What about 10 and 4, x to the 10th? So again, I have to make sure I have the same base to be able to do this. And then what I'm going to do is I'm going to subtract. So I get x to the 10 minus 4 gives me 6. So I will often use that division sign like a minus just as a reminder of what's going on. So for the 5s, so I have two separate problems now. I have 5 as a base. So 12 minus 7 is 5. And we'll have y's as well. So 20 minus 8 is 12. All right, so I kind of covered up the last one here, and this is to work in reverse, make sure we got the idea. So what would end up with a to the 7th, b to the 3rd? So I definitely need a's and b's on the top and the bottom. Okay, so that means for the numerator, I need a number greater than 7. You said 11? Okay, so 11 minus what gives me 7? Well, that's 4. Okay, and then b's, I'm trying to get 3. So let's go with 8 here. So 8, I'd have to subtract how many to end up with 3, and that's 5. So this would result in a to the 7th, b to the 3rd. So it's pretty good. So how can we communicate that rule? So if I am dividing with the same base, what should I do with my exponents? Subtract them, and I should start from the numerator to the denominator. Okay, so that's our algebraic rule that we came up with as we work with those. All right, so if we need a numerical one, right, we need 3 to the 12th over 3 to the 4th. Right, that's going to be 3 to the 8th. Okay, we want to subtract. All right, so what happens if I do this? If I do 2 times 2 times 2 and I put it over 2 times 2 times 2, well, that turns into 1, that turns into 1, that turns into 1, so I get 1, right? Because it's the 0 exponent, right? Anything to the 0 power is 1. So this turns into 1, and as long as I have the same base, if I divide the whole thing out, it becomes 1, so I get 1. Anything to the 0 power should equal 1. All right, anything to the 0 power is 1. All right. Distributed rule for quotients. Okay, so that means this 4 goes to the top and the bottom as we work with this. So this would be 1, 2, 3, 4, 5, 6. So 3 to the 6th, this is 5 to the 6th, or it could have looked like 3/5 to the 6th power. Those are equivalent as we look across the way here. All right, so we're going to use some of that idea. Let's jump down to this one. So that means I need 2 to the 3rd, x to the 3rd, and 9 to the 3rd. Okay, so we're going to distribute not only to our top, we talked about that one earlier, but also to the denominator for anything else we need to do. All right, so here we wouldn't know which one's going on. So it is a to the nth, b to the nth, and that's good enough for our distributing rule for quotients. Quotient, remember, that means divide. So if we have anything else going on, we want to make sure we have that. So I might have 3 here, I might have an x there, and I can even say it's to the y power. It really doesn't matter what we say it is. We just have to make sure we distribute that power to both of them in the numerator and denominator. And then, of course, the power rule. This is the one, it has to do with a power to a power. That's why we call it the power rule. So that might be answering a question down here. Power to another power. That's when we're actually going to multiply. So you see 2 times 3 does give me 6. So if I have 5 to the 3rd and I want 4 of those, so instead of writing this out over and over, we did see this in Algebra 1, right? This is supposed to be a brush up, not brand new. So we're going to say this is 5 to the 12th. Okay, so how can I get 7 to the 12th? Well, that would be 7 to the 2nd to the 6th. Can you give me another one? Okay, flip-flop them. What about another one? 3 to the 4th, and we could flip-flop those. So you can see we're just going to work with all the factors of 12. So this must have been x to the 6th. We have 1, 2, 3, 4 of them. So that ends up with an x result of x to the 24th. That would be a lot of them. And we want to use distributing with this as well. So as we take a look here, this becomes a power to a power. So 3 stays the base, but now it becomes to the 15th, and y is our other base, and that's to the 6th. Okay. And this one's too big to write out. We're not going to do that. Okay. But I do need to multiply these two together. So it'd be a. If I double 32, it's 64, and put a 0 on it. Nobody should have to write that out. This was even silly to put on here. Okay, but power to a power is when we're going to multiply. So we go to that basic rule here, x to the mth power to the nth power. What should I do with m and n? I should multiply them, right? How's it different from the product rule, right? The product rule, remember that was multiplying the two bases that were the same, so I could add those. Okay, so the big difference that we'll see here is you have two exponents, means you should multiply them. If I have two bases, that means I should add those exponents. All right, negative exponents. Okay, so this is what happens if you end up with the extra or leftover ones down here in the denominator. Okay, so that means they are on the bottom. And what we could do is bring that up top. So we're going to use that subtraction rule first and say this should be a. I have 5 more on the bottom. So it's the negative fifth, okay, which is 1 over a to the 5th power. Okay, so how could I end up with 4 to the 8th power on the bottom? Okay, so that means I need 4 on the top, 4 on the bottom. But I need to have 8 more on the bottom. So let's make that 10 and let's make that 2. Right, so when I subtract, I get 4 to the negative 8th, which means 1 over 4 to the 8th power. Okay, so whenever I use my division rules and I subtract, my answer always goes in the numerator. And then if it's a negative exponent, we're going to flip it over one more time to get our final correct answer. Okay, so this must have been 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. So this must have been x to the 3rd, x to the 7th. We have a y. Okay, so the y doesn't have anything going on with it, so it's going to stay there. And what happens with the x's is we notice we have 4 left over on the bottom. So we're going to signify that by saying it's x to the negative 4th. So those are done. Now, just as a side note, we never leave negative exponents in our final answer. So this will turn into y because it's to a positive, and we get x to the 4th in the denominator. Okay, so this answer as a fraction is always going to be what we're after as we take a look at these. All right, looks like a couple more left here. So a, right, 4 minus 9, so it's a to the negative 5th. 5 minus 12, so it's b to the negative 7th. So our final answer is going to be 1 over that, and we're going to change those out to positives now. All right, looks like we have different bases this time, but remember, what is anything to the 0 power? That's 1. Okay, so this becomes 1 over 25 to the 4th power, which we can't have that without thinking about what happens here, right? So if it's on the bottom and I'm going to move it up, right, I'm going to make it a negative exponent. And if it's on negative exponent on the top, I need to move it down and make it a positive. So what's a negative exponent mean? Right, that means we're going to work with the reciprocals. So that means x to the negative 2nd is 1 over x to the 2nd. So to make sure we see that as a reciprocal, I'm going to make it over 1 here so we can see what's happening. Now, in the other case of it, so if I have 1 over, let's say, 5 to the negative 2nd, that does become 5 to the 2nd over 1, or just 25. Are positive expressions with negative exponents negative? Okay, so that's what we had here with the 5. So the 5 is positive, has a negative exponent. Does this become negative? No way. No, it has to do with the location in the fraction. It has nothing to do with whether it's going to be positive or negative. All right, so what are we going to do here? We got 1 over 2 to the negative 3rd. We're going to call that 2 to the 3rd over 1. So it's just 8, right? 2 times 2 is 4, times 2 is 8. So that's our rule. Okay, we have plenty of these rules written up here. So if you have those jotted in, you're in good shape. I don't know how many more rules we need. Okay, so that reviews all of our Algebra 1 exponent rules. We're going to use those to simplify radicals and continue working on those in various different ways.